Alright, so here we are at section 7.4, matrices and systems of equations. And I told you at the beginning of this chapter, the title of this chapter is Linear Systems and Matrices. And we haven't even started talking about a matrix yet, and we are almost halfway through the chapter. Here we start seeing what a matrix is. And for right now, a matrix is going to be a rectangular arrangement of numbers in rows and columns. All right, and plural of matrix is matrices. Comes up quite often. So you're going to have, and it doesn't necessarily have to be a square, it's going to be some amount of rows and some amount of columns, and all of these places are going to be filled with numbers. All right, so, and if there's no number there, you're actually going to put a 0 there. So there's going to be a number in every single row and column the entire way through. I will show you some examples. The way this matrix, because there are m amount of rows and n amount of columns, it would be considered an m by n, right? Matrix. M as in matrix, n as in Nancy. M by n. All right. So matrices are defined by the number of rows they have, followed by the number of columns they have. So if you have 3 rows and 2 columns, that would be a 3 by 2 matrix. That is known as the order of the matrix, and we're going to talk about that on the very next slide. Above, these are all, when you need to talk about, like I want to talk about the entry in row 3 that is also in column 2, that would be subscript 3-2, just for clarification. So that would be this one right here, because it's in row 3 followed by column 2. Now I know which specific point we are known by, and if m is equal to n, meaning it has the same amount of rows and the same amount of columns, then it's known as a square matrix. Okay, so here we have just a couple quick questions. Determine the order of each matrix, which is a fancy way of saying how many rows does it have, how many columns does it have, and you write it here. Well, there is only 1 row followed by 5 columns. So this would be a 1 by 5 matrix. Now, even in this next matrix, there are only zeros, but there are still 2 rows and 2 columns. So this one would be a 2 by 2 matrix. In the bottom here, I have 3 rows followed by 2 columns. So 3 by 2. Rows always comes first, columns always comes second. So the real reason we use a matrix is because a matrix is to represent a system of equations. All right. So while in the very last section, you probably solved problems like this many times over, and every single time you were copying over x's and y's and z's. And a matrix is just a more efficient way to do the problem where we don't need the x, y's, and z's, because you know what? Everything in column 1 is going to be an x value. And if you notice on this slide right here, what I have is my linear system on the top and my augmented matrix for the exact same linear system. All right, so my first column has all x's. All I write in the matrix is the coefficients, and because it's a matrix, I know everything in the first column is x's. I know that everything in the second column, right, they're all y's. Everything, the coefficient to everything in the third column is a z, and everything on the end is after the equal sign. So this is what's called an augmented matrix. So I know here's my equal sign, and this is going to be just some constant number at the end. There's 2 types of matrix notation. An augmented matrix has the number after the equal sign. A coefficient matrix is exactly the same, but if you notice, a coefficient matrix leaves out that last column, that piece after the equal sign. So while just to practice order a little bit, this would be a 3 by 4 matrix. Down here, we have a 3 by 3 matrix. So that's a quick definition for matrices. And here, this is a linear system. Let's write it as an augmented matrix. Right. Well, I'm going to write all of my x's in the first column. 1, the next equation doesn't have any x's, and the coefficient, x's. Next column over, all of my y's. 3, -1, there are no y's, so there's going to be a 0. Z is in my next column, 0. 4, negative 5, and here's my augmented matrix, so I need after the equal sign 9, negative 2, and 0. Sometimes in your book you will see a little dotted line here just to show that that's an augmented matrix. Only augmented matrices would have that dotted line there. Okay, so the nice part about matrices is they follow these same exact rules we learned last section. When we solved linear systems, we did it by interchanging rows. We did it by multiplying a row by a constant, and we did it by adding a multiple of one row to another, although I'd say definitely 3 is the one we did the most. The other two come up occasionally. We're still going to do that, except now we're going to do it with a matrix where you don't end up writing your variables over quite so often. All right, so here we have an augmented matrix. Remember, this is just a fancy way of saying it's a system, and we're going to solve. And it's going to look very similar to the linear systems that we solved. Our goal is to get 0 here and 0 here. After we do that, we're going to want to get 0 here, and we will then be able to use back substitution. So let's give it a shot. If you think of this like last section, I'm going to keep the top row the same. All right, similar to how I kept my top row the same for most of last section. And what's going to happen now is I'm going to add row 1 and row 2 together. And if I add them together, that's going to be 0, 1, 3, and 5. That gets the 0 that I wanted here. That gets me the 0 that I wanted. This is 0. That's good. Now the next piece is try to get a 0 here. Well, clearly just adding the top row and the bottom row isn't going to get a 0 there. I'm going to need to multiply that top row by something, and I hope you're saying, if I multiply it by negative 2 and then add it, great, I'm going to get 0 here like we want. So we just have to remember everything gets multiplied by negative 2. That's going to be second column. That's going to be 4 plus negative 5. All right, that's negative 1. That's going to be negative 6 when I multiply, and then I add it with 5. Another negative 1. Negative 18 plus 17 is negative 1. Okay, the last part to this is we need to get 0 right here. And how are we going to do that? Just like in the last problem, we use the second row to get 0 in the bottom row. So similar to last section, the top row doesn't change much. Middle row on this step, in fact, just like last time, isn't changing. What I am going to do is, to cancel out 1 and negative 1, all I have to do is add those. So I'm really just combining these two rows, because if I add 1 and negative 1, I get the 0 that I want right here. All right, so that leaves me with 3 negative 1, that's 2, and 5 and negative 1, that's 4. So I now should be able to say 2z equals 4. So in my head, I know that z equals 2. So the even easier way to write this would be 1, I don't need the equal sign, followed by a 2. Because that now tells me that my z is equal to 2. And if I know z, this is the point where we use back substitution. I'm able to back substitute. And so if at this point, it might be a good idea to write this as a linear system. X minus 2y plus 3z equals 9. That would be y plus 3z equals 5. And this would be z equals 2. We've actually solved this linear system before. We just never did it as a matrix. Here, the back substitution is exactly the same. It would be y plus 6 equals 5. So here, y would equal negative 1. And now I can substitute it right into this top equation. X minus 2 times negative 1 plus 3 times 2 equals 9. So that's going to be x plus 8 equals 9. So x equals 1. 1, negative 1, 2 would be the solution to this matrix. And really, a matrix is just another way of a linear system. All right, so we've talked about row echelon form. Row echelon form is getting those 3 zeros we've used in a very specific, those 3 very specific places. The rules to row echelon form are any row of all zeros, meaning not a single number other than zeros, has to be at the bottom of the matrix. That happens occasionally. We haven't seen it very often. happened in our when we had many solutions in the last section. The first non-zero entry of each row is a 1, and that's called the leading one. All right. So if you notice going back, this is right here. This would be a leading one, and a leading one. So, and the last part to row echelon form, the leading one in a higher row is always further left than the leading one in the row below it. And if you think back, that makes sense. Here's my leading one. It's further left than the leading one in the row below it. And my last leading one is furthest to the right. That's essentially what row echelon form is asking. I do think it's worthwhile. There are like 6 examples on page 493 where you could take a quick look. It gives you some examples of what is row echelon form and what is not. They're quick. It's worth a glance. All right, and we probably don't have enough time to solve this matrix on this video, so we will solve it in our next video.